Hello everybody, hopefully you all are doing well and staying safe. We'll continue with our lesson 5, electricity and magnetism. Hopefully you have your books with you so you can take notes and prepare questions. So as you know, we were talking about circuits. We were talking about AC current, DC current, and now we come to different kind of circuits. First we come to the CV circuit. Remember, in a CV circuit, we took it before also, there is only one path for the current electricity that can flow. There is only one path, only one road, okay, through which the electricity can flow in a CV circuit. For example, a flashlight, the electric charge flows along a single path, only one path, from the batteries to the light in bulbs. Now each battery here in the flashlight supplies more energy that causes electric charge to flow. So for example, the light bulb receives the sum of the energy that comes from the two batteries, the total energy that comes from both the batteries. Now this energy is measured in volts, capital V. Now because each battery has 1.5 volts, the two batteries, the sum of them, 1.5 as you know, will be 3 volts. A higher voltage causes more electric charge to move through the light bulbs. Now also remember that light bulbs and many other devices act as resistors. Remember, we'll learn about resistors, the things that make the current flow slower. So in a CV circuit, the total resistance is the sum of the resistance of the individual device. For example, the two identical light bulbs together in a CV circuit will have twice the resistance of either bulb by itself. So they're actually they are resisting the flow of electricity, making it slower and transforming energy. As you can see, thermal or heat energy is also being produced. So since two bulbs here, so the resistance is going to be twice the bulb by itself. On the other hand, parallel circuits, they are actually, there's no, as you can see here, there's not just one path, multiple paths along which current electricity can flow. For example, in a string of lights wired in a parallel circuit, if one bulb burns out, the other, they keep on working. The electric charge can flow to them because there are many paths in it. But if we come to the CV circuit, if one of the bulb flows out, because it's connected only one path, this one also will will turn off. So but the parallel circuit, on the other hand, is different. It has many paths, due to which if one bulb is switched off, the others will keep on working. Parallel circuits are used actually everywhere that we use electricity, for example, including homes, offices, stores, markets, many places. And if any other device on the circuit burns out, as we said, because there are many parts, the other will keep on working. Now short circuits, sometimes an additional type of backup is added to protect against high levels of current electricity. Now a short circuit, or on the other hand the ground fault circuit, now these are circuits that's a path for current electricity that has little or no resistance. Current flowing in a short circuit can reach dangerously high levels and will also generate heat. Now there is a device called fuse which prevents dangerous levels of current from continuing to flow through a circuit. So fuse contains a piece of metal that when it melts, it is heated. So this melting breaks or opens the overloaded circuit. Sometimes it happens in your homes. For example, if there is more load on a circuit, what happens that it triggers out, it closes off because of the more load on it. The circuit just opens up, so everything in the home just stops working. In electronic devices, there's something called fuse. This fuse burns out if there's more current electricity coming than what it requires, and due to this, then you need to change that fuse. We all have used magnets at home or school, to attract and pick up objects which are made up of metal, such as iron or steel. You can use magnet to push and pull things without even touching them. So magnets actually are surrounded by magnetic field. That is an invisible area where the forces of magnetic attraction or repulsion can be detected. Scientists think that magnetism comes from the spinning motion of electrons in a magnet's atom. Each atom behaves like a tiny magnet. Because these atoms, because of this, the atoms of iron and nickel and cobalt, they tend to point their magnetic field in the same direction. These elements actually form strong magnets. Magnets are actually surrounded by a magnetic field. Magnetic field is, that there is a force of attraction between the poles. That's called the magnetic field. The area with, actually this is an invisible area, you cannot see it. The forces of magnetic attraction here, or the repulsion that can be deducted in the magnetic field. Plus properties of magnets, as we see here, the old magnets, they have two poles, a north seeking pole which is N, and then the south seeking pole which is S. For example, if a magnet that is suspended so that it can spin freely, the magnet's north seeking pole will move and turn towards Earth's north magnetic pole. The south seeking pole of the magnet will point towards Earth's south magnetic pole. And you see that a compass, if you have ever used a compass, the needle in the compass, you see that it's a magnet that rotates to point towards the north magnetic pole of the Earth. Now, the south pole of the magnets repel each other, and the north pole of one magnet is attracted to the south pole of the other magnet. We know all this is a simple theory that the same poles will repel, while the opposite poles do attract the iron or cobalt or steel pieces. Electromagnets, the flow of electric current produces a magnetic field. A wire carrying electric charge has a magnetic field surrounding it. It can even pick up certain metal objects just as common magnet can. So you have electromagnetism, and now we have here a piece of metal which is coiled up with wire. This is a magnet and it's joined up with the battery. Now this iron core is placed within the coils, as we see. Now the magnet becomes even stronger because it's connected with the battery. A device that is actually magnetized by current electricity, that is called the electromagnet, such as this one, because there is current electricity provided in it. Electromagnets are convenient, they're easier to use because their magnetism can be turned on and turned off by stopping or starting the flow of electric charge. So that is why it is easier to handle, because you have like a button switch, turn it on and off. And you see here the electromagnetic field. On the other hand, the same thing as the magnetic field, how much stronger the push and pull can be. Now, applications of electromagnetism. Electromagnetism can actually be found in many things around us, from motors to sound equipments to mobile phones to televisions, even some trains. Electromagnetism actually is used all over most of the devices that we actually use. Plus, electromagnetism is also used in the role of medical life. Doctors use a technique called the magnetic resonance imaging, or the MRI, to produce image of human tissue. You know that sometimes there are things that are more complicated and they are not visible even in X-rays, so then the doctors go for the MRI scan. So the abbreviation for MRI scan, remember, magnetic resonance imaging. So in an MRI, the patient actually lies inside a long tube. You've seen an MRI machine here. It's a long tube and is surrounded by electromagnets on both sides. So in the patient's body, the nuclei of certain atoms tend to line up with the magnetic field. So when radio waves are, when it's the MRI machine starts, the radio waves are beamed at the patient's body. The hydrogen nuclei gains energy and sends out signals to the computer detectors. So that was a lesson for today. We'll continue up with this lesson since we did not finish it yet. So please review. If you have any question, feel free to ask. Thank you once again.